Nathan, are you there?
Yep, I'm here.
Yeah,
Okay.
so you are the TA for today, right? And so Chahya is here. Yeah, I think you met Nathan
Yes,
when you
yes.
came to Indonesia.
Yeah.
So
I think the last time was 2 years ago.
2 years ago, right?
Mhm.
Okay, turning live on YouTube. Okay.
I think there are some questions on the chat,
Mhm.
but those questions have already been answered in the introduction. So how are you going to answer that?
Well, yeah, of course, the lecture slide will be shared later after the class. Okay. We're also recording this on YouTube because I also want to share the link to the lectures. I mean the in ITB.
Ah, okay.
Yeah.
You mean those who are not in this event?
Yeah, those who are not in the events, but we'll just share this to the ITB's lecture in the Faculty of Mechanical and Aerospace Engineering only.
Okay. Noted.
Yeah, so Nathan will open this class first, and then he will hand it over to you.
Okay.
Okay.
What time is it?
It's 1 minute before the class, but maybe wait a minute or two probably. So you want the students to turn on the video because you don't want to stare blank screen, right?
Yeah, I think for sure. Let me check. Teresa is- Oh, hi, Tim. I saw your video. I was just like browsing and I see Tim.
Oh yeah, and I was there in his background too. See that?
Oh, oh, that's true. Yeah. Mhm.
Anyway, Rhea, I don't know
Mhm.
if it's the right place to tell this, but Tim just got married.
Sorry?
Tim just got married.
Ooh, okay.
I'll
I'll
give you
catch
an
up with
update
it.
later on, for sure.
Okay, I'll be waiting for that.
Okay. Maybe I think we can start to make sure that we are on time. Yeah, so I think we are good to go. So all
Okay.
recording. So it's already recorded. Okay. YouTube. Okay. So everything's fine. So we're good to go. So Nathan, you can start.
Okay, so welcome everyone to MDO-ML, and this is our first class. So we got Dr. Rhea Patricia Lim. She's from Hong Kong University of Science and Technology, and she's going to have a talk with us about the introduction to modern tools in engineering, design, and optimization. So first of all, I would like to remind you to stay muted during the session, but at the end of the session, we will have a Q&A session, so you can open your mic at that time. So by now, Dr. Rhea, you can start your presentation, and we will very delighted to have you with us right now.
Okay, thank you, Nathan.
Okay.
Okay, so okay, hi everyone. I'm glad to be here. For those of you who are in ITB, I usually had an annual visit for research collaborations and discussions, but unfortunately, these 2 years I cannot visit. But anyway, so I have the honor to start and to end this international virtual course. So I hope you enjoy my talk. Okay, so first, let me just introduce myself. So currently, I'm an assistant professor at the Department of Mechanical and Aerospace Engineering at HKUST. So education background, you can read it. I don't need to read it by one. But I think what you can see here is that my backgrounds involve computational engineering and aerospace engineering as well. So my PhD thesis topic was actually multidisciplinary design optimizations in aircraft design involving surrogate modeling. So I'm still doing aerospace computational research with applications in aircraft design and air transportations. So currently the goal or the ambition is to combine the two. So as you can imagine, aircraft design, for those of you who are not yet familiar with aircraft design, I think I will touch upon that topic to be my examples as well in this lecture. So you will appreciate the fact that it is really complex, and you can imagine air transportation is also another complex system. So how to combine them together. So it's going to be extra complex, but it is a good example of a real world engineering problem. So preliminaries, I think just want to mention that in this lecture, I don't think I will spend the whole 2 hours, but anyway, in the 2 hours that we are going to spend here, I'm just going to give you a very brief introductions or the concept of engineering design. And as you can see, we are going to touch upon modeling, optimization, sensitivity analysis, surrogate modeling and machine learning. So those are the topics, or those are the big topics that we are going to cover in the next 3 weeks. So I'm going to briefly introduce a concept as well as to show you how they are put together. So as you listen to my lecture, I hope you can get an idea of how those components MDO components are related to each other. And once you have a rough idea, then when you go through the more detailed lecture on a specific topic, then try to always put things in a context, in the big picture. So as you saw, my background is mostly aerospace engineering, so I will use a lot of examples in aircraft design and aerospace engineering context. However, feel free if you want to share some examples from your own research areas. And I also invite you to actively think about how the concept that I explain and the examples that I will give in this lecture can relate to what you are doing in your specific research topics. So class dynamics, your active participation in encourage. Yes, you should mute your audio, but I would invite you to ask questions if you want to, or feel free to write in the chat, but I might not be able to read it immediately. But if you have a pressing questions, you are allowed to ask me or interrupt me. It's up to you, or you can also wait until the end of the lecture. So I'll try to be flexible. And also I will ask a few questions. So I hope you can answer those. Don't be too silent. I know that the active participation might not be counted in your grade, but if you are my students, if you're taking my class, then it will be counted. So so you better do that. And yeah, feel free to turn on your video as well. I'll be happy to see faces instead of, like black screen. Okay. And again, the lecture notes will be shared by the main organizer. And I think Nathan will help, or Pram already helped, upload the notes. But please do not distribute the slides to the public. I think that will apply to other lecture notes as well. Okay, let's get started. So here you will see some of the topics that we are going to cover today: design, modeling, optimization, sensitivity analysis, surrogate models, and machine learning, and final remarks. So what is design? So, when we think about design, some of us might think about design as having artistic values. So while that idea is correct, but when we talk about design, we go beyond artistic values. The design first and foremost needs to serve an intended purpose. So design itself can be geometrical, physical, or mathematical features, but they are actually created or they are synthesized to explain a function and needs to have a purpose. So not just for decoration, not just for the artistic values. So it needs to have a preconceived goal. So you need to, you don't randomly generate a design, but you need to know what you want to design. Requires planned actions to prepare. And you will see that when we start talking about engineering design of complex real world engineering problems, then a lot of planned actions need to be involved. And it needs to serve a specific purpose. So what are the key drivers in design? So anybody wants to try either by chat or, what do you think if you need to design something, if you need to start designing something? So what will be the first thing that you think about? There are a lot of performance, cost, metric of objective data. Oh, a lot of things. Okay, so yeah. So basically, I wouldn't read them one by one, but thank you for the inputs. So basically, I see that the two requirements. Yeah. So basically, the first thing we need to think about is obviously the purpose or the requirements. So, but even for the key requirements, we can have a major requirements, specific requirements. And then we also need to consider the operating conditions. Like, for example, if we design a product where it is going to operate. Like if you design something to be used in the desert and something to be used in Alaska, I think they will have different, requirements. Availability of materials, because once you design something, you have to make sure that you can actually deliver. The same goes with manufacturability. So if we look at these chairs, so anybody wants to say either verbally or by chat, so what will be the key major requirements and what will be the specific requirements? So it can be anything, like whichever you want to answer. Okay, you can see the chairs, like the different images of chairs, right, on the right hand side. So what are the similarities and differences of these chairs? So somebody mentions about the structures. It can be seated, the intended use, where and for who. That is actually a good examples, because you will see that wheelchairs, obviously, it is not just designed for everyone. It can be used for its function. That is correct. Yeah, so basically, if you see the chairs here, they all have the same function, which is, we need to be able to sit on it, whether it is a deck chair for, by the swimming pool, or whether it is a wheelchair for elderly or for people who are in need of assistance. So all of them have similar functions. So can you give me examples of the specific requirements of any of the example here? Or you can also give examples of different operating conditions. Write something. User durability. Yeah. Oh, seating capacity. That's a good observation. Some of the chairs are only for one person, and some others are for 2 or 3 people or more. There's a stress loading, so the strength will be different if you design chairs for kids and if you design chairs for adults. They will have different strength requirement. The temperature. Yes. So basically, and you can also see that The materials might be different. Like for example, if you design a chair to be used at the beach or by the swimming pool, you need to have a water resistant materials. Mobility, that's a good example. So some chairs, like a heavy sofa, you don't they are heavy because you don't need to move them around. But there are other things that for example, if you go to a conference, then like they stack the chair and they have to distribute it quickly. Yeah, so wheelchair is a specific example as well, that it needs to serve a very specific purpose. So as you can see, so first, thank you for all the answers, and it is interesting because I think when I saw the names, it seems like they came from all over the world. So so it's fun to see you all here and to participate. So yeah, basically, so this kind of concept also applies when you design an aircraft, when you design an automotive system, or when you design a bigger system, an air transportation system, which is not tangible. So first you need to have the key requirements, and then you need to know where it will be used and how it will be used. Oops. Okay, so that's about design. So it's more general, but what about engineering design? So engineering design, it's more systematic. For like actually we can design a chair without much thinking, right? Like I mean, if it is, especially if the loading is low. But when we talk about engineering design, we talk about the design of something even more complex. So usually we think about engineering design as a decision making. So it is you need to have the decision making paradigm in the design process, because the engineering design will involve analysis, systematic analysis, on how are you going to design a product or a system that can serve your purpose. So by the time we reach this point, I assume that all the designers, engineering designers, will have the purpose what you want to design. So in engineering design, it will involve systematic analysis to evaluate the performance of different design alternatives. And you also need to engineer a way to be able to select the best alternative, the best options, of course, considering the constraints that you have. So yeah, so in a way we can think about design as a decision making. So in decision making, you need to have a tool to be able to assess the different decisions and then to make the best, to find the most suitable one. I already mentioned that when we designed, we don't always think about something that is tangible. It's not only a product. So for example, when we saw the chair example, obviously the end product will be a chair. But when we talk about aircraft, if you think about it, aircraft is not just one product. It is actually, for an aircraft to be able to fly, it is a collection of different subsystems, different entities that perform together and to serve the unified goals or purpose. So for example, if we talk about an aircraft system, we talk not only about the physical structure of the aircraft, which by the way has to be carefully designed, and we need to have for example, the propulsion system, which again has to be carefully designed to be able to power the aircraft to fly. And then you have the avionics system, the control system. So all those are involved in the aircraft as an aircraft system. So and then system can also be something that is completely intangible. So for example, air transportations. How do you control the flows of aircraft from one place to another? A network of air transportation. So remember that when we talk about design, it's not only about the product, but it can also involve a system. So that shows how complex it is. So if we look at this, one thing that we need to have is an abstraction to describe the product or service or the system. So in a way, we can think about the abstractions as something to represent whatever you want to design. So for example, you might need to have a computer modeling for the chair that you want to design, or a more complex model for the aircraft system that you want to design. So that's how the mathematical model can help in the process. So a good design brings knowledge and experience together. So in a way, in design process, from what I learned and from what I have observed, a lot of experience, past experience really helps. So as students, you learn a lot from textbooks and from your lecture, from the lecture notes. However, if some, I believe some of you are already in grad school, you will learn that, you know, like the textbook alone are not sufficient. So what I see in aircraft design is it is hard to say that, you know, somebody is an aircraft designer, because it needs the accumulations of experience. And you know, from people whom I know, I can only mention a few aircraft designers who have gone through the whole process. So that is an accumulations of what you have learned, what you have experienced, as well as what other people have experienced. So case studies are very important in studying a complex system design. And unfortunately, sometimes in improving the design, we learn from failures or accidents. So one example here, so I showed a picture that that is a comet aircraft, the Havilland comet. So you can take a look at the pictures. And so basically what happened was in 1954, within 3 months, there were 2 crashes. So the entire Comet 1 fleet was grounded. So do you know why, what was the cause? Can you guess? What do you think was the problem? The windows, yes. So non-round, yeah. So basically, this is just an example of how aircraft accidents led to aircraft windows design change. Oops. Yeah. So basically, so thank you for all the answers. Yeah. So basically, the if you look at the windows compared to the windows of most of the aircraft, commercial aircraft that we know now, they have like rounded, you know, windows with rounded edges. But back then in the 50s, in the 40s, they didn't care so much about this. So as you can see, they had square windows. So that actually, you know, like caused high stress concentrations. The fatigue loading actually led to the accidents. So this is an example how a series of accidents, you know, led to the changes of now the windows that we know have rounded edges, and they also put crack stoppers installed between frame cutouts. So this is just an example. There are other examples as well. So other key aspects in designs, you know, first, of course, you need to know about the system. You need to know about how to model it, which we are going to talk about later. But the other key aspects, first is the measure of merit. So measure of merit is a bit different from the requirements. So requirements are usually will be stated, like, for example, this aircraft has to be able to carry 100 passengers covering distance like 5,000 nautical miles or something like that. It will be clearly specified. But measure of merit typically refers to what the customer or the user will want that are not explicitly mentioned. In some cases, actually, aesthetics can also be a measure of merit. Another thing is, you know, maneuverability. In other words, you try to guess what the pilot would want, not just the customer, not just the airlines, but you need to guess beyond. You need to be able to see beyond the specified requirements. And in design, especially for real world engineering problems, none of the design will be done by one person. So teamwork is very important. You know, typically we will have what we call the integrated product teams, or the IPT. So it needs to have a coordinations and integrations between different experts. Because you know, like a complex problem will need to touch upon different disciplines, and then you need to have a system engineers to coordinate or orchestrate the whole integrations. And another thing is that communications is very important, because you don't want to have any design failures or miscommunications causing design failures or other problems. And by communications, is not only to communicate among the team members, but also to communicate, to be able to present your designs, or how to defend your designs to other people. So I guess the reason why I mentioned this is, as most of you are learning engineering, so you have to realize that once you start working in the real world, once you do research in the actual research setting, whether it's academia or industry, these three things are very important for you to realize. So again, textbook lessons are not enough. Challenges in modern engineering designs. So first, actually, it's driven by greed. As you can see, like people always want something to be better, faster. Like you just look at your mobile phones, right? Think about the mobile phones that you had 10 years ago. And what your parents had 20 years ago, but before that, you didn't even have a mobile phones, or at least it was not as common. And when, you have witnessed the rapid changes in the requirements. Like the customer would want more and more functionalities. The customer would want the size to be smaller, but actually currently I think they also want it to be bigger. But anyway, so the camera was introduced only in the past, I don't know, 10, 15 years. Before that, people didn't think that you would have a camera in your mobile phone. So these are the examples that the requirements and the measures of merit keep increasing. And also there are more regulations, then there are more design aspects. So currently, I think what is popular is the environmentally friendly everything, eco-friendly everything, or green everything, green aviations, environmentally friendly aircraft, or even environmentally friendly food utensils. Or so those are the things that change, shift the paradigm in design as well. Not just functionality, but now we have to start including all this into the process. So that will complicate the design process as well. Okay, so for example, in the early design, aircraft design, I think we only care about the functionalities, that the aircraft just need to fly at the beginning. And then the second stage, the aircraft just need to carry some payload, whether it is mails or whether it is just two people. But after air transportation became more popular, became more competitive, so they start thinking about the cost. So initially, they only thought about the functionalities, and cost was only added as a consideration once the design was locked in. But starting in the 1960s, they start including the life cycle costs, the acquisition costs of the aircraft early in the design process, which again, it complicates the design process. So for example, if at the beginning you just want to minimize aircraft weight or maximize the aerodynamic performance, but later on you have to consider the cost. And nowadays it's not only the performance, the cost, and also the environmental impact of aviations. Some of the characteristics of real-world problems. Yes, I think there's a comment about the Second World War. You will see. I will also discuss about see the evolution of design with aircraft design example after this. The characteristics of real-world problems: first, complex and multidisciplinary. That means there are more to models, and then how the different disciplines are coupled together. So that is also challenging, and you will learn more about this in the multidisciplinary design optimization MDO lecture by Professor Nathalie Bartoli. I believe it will be next week. Modeling complexity. This might be overlooked, but if you think about it, when you try to combine different disciplines, some might have like really fancy modeling. The other discipline might have very rudimentary modeling because it hasn't been advanced as much. So one example that I can give you is, let's say you are trying to design an amphibious aircraft. So amphibious aircraft is an aircraft that can take off and land on the water. So amphibious aircraft, obviously, it has wings. And how to design wings, it has been covered and it has been explored by different researchers. So it's quite advanced. However, if you think about amphibious aircraft, the hull, which is the bottom part of the fuselage, will need to be specially designed because it needs to contact with water. Hull modeling is not as advanced as the wing modeling. So these are just some example of the challenges of how to combine the models for different disciplines together. And then on top of the modeling, the next question will be: do you only design your product at the nominal conditions, or do you want to consider the variations of the operating conditions? So, in aircraft, for example, do you consider only at the cruise, or do you want to optimize the aircraft at more variations of operating conditions? And then on top of that, you have the variability, the randomness in the operating conditions. So these are just the characteristic of real world problems. And you will see that in the different lecture topics, you will touch upon all this part. Okay, so again, we'll just quickly go through this. I'm not going to, it's not a history lesson, it's not a storytelling, but I think this is just to give you an idea of how designs evolve. So at the beginning, you see something really primitive. And to be honest, these four were before the first flight. So, the main purpose was to try to fly. And then we had the first powered flight, the Wright brothers, 1903. But if you know how far it flew, the maximum range was 120 feet. If you want to imagine how short it is, 120 feet is actually shorter than the space shuttle total length. So it is, they literally just designed it for flying. And then we have the mail plane, the First World War, Second World War. So as you can see, the World War really spurs the design of the aircraft. And in the early commercial flights, DC-6 Lockheed Constellations, and then a 747 was considered as one of the milestone in aircraft design. It was the first twin-aisle 4-engine super jumbo aircraft. It was designed in 1970. And the nickname was Queen of the Skies, and I think you know why, because it was the first jumbo jet to fly. And there are a lot of interesting stories about this, but if you want to know more, then attend my class at USD, not here. Yeah. So this between 1970 and 1990, there are a lot of changes in aircraft design process. So the first, there's a shift in the engineering jobs because due to the oil crisis and the sudden government funding cut and also the end of the Apollo program. But at the same time, there's an advancements in computing technology and numerical techniques. So they start seeing the computer-aided design, and they, that's in the 70s to 90s. If you are aware of the air transportation, it was also the passing of the Deregulation Act at the US, 1978. So basically, airlines became more commercialized. So, air transportation became more competitive, and the bottom line is more people flew. So, because there are more people flying, so there are more additional design considerations as well, including cost, performance cost, reliability, maintainability, and other aspects. And also, there are new technology introduced, like fly-by-wire, computerized management information, etc. So this 70 to 90s is a big shift in aircraft design. So do you know what aircraft type that first used a CAD or computerized this? Triple seven, yes, it's correct. Either you have seen my slides before or you know it, but anyway, thank you for the participation. Yeah, so 777 was the first aircraft developed by CAD and CAE. So basically the 777, but it's not only that, it is also the first aircraft where the aircraft manufacturer Boeing actually invited some of the potential customers to define the mission requirements. So previously it's more one-sided. That the the aircraft manufacturers will design something that they think is right, and then they sell it. And then for 747, actually it was single customer, started with Pan Am, and 777 was the first to actually invite more potential users to specify the mission requirements. And A380, the first full double-decker passenger aircraft, and 787, it was the first with more than 50% composite materials. So we can talk more about how each aircraft is different. But I think what I want to show you is that from this example in aircraft design, you have seen how things really advance rapidly. So all these changes were also assisted by the rapid advancements in computing technology and numerical techniques. So all these new designs were enabled by MDO. That is the bottom line. But like demand in air transportation increased rapidly. Like people want aircraft to fly faster and to be more environmentally friendly, and basically people always have endless demands of what kind of products they want to have. Yeah, so essentially air transport has become cheaper, safer, and busier. So if you see some of the example here from different decades, you can see that the basic shapes are the same, right? Like it's a tube and wing configurations. However, with the optimizations that are introduced in different parts of the aircraft, there are actually a very big difference between the DC-3 performance and 777 performance, and some of the newer variants of the different aircraft types. So all those are again helped by the optimization process. And as already mentioned before, so those we already have really kind of optimized aircraft in terms of the performance. However, now the focus shift to sustainable aviations. Sustainable in terms of environmentally and economically as well. By sustainable, we talk about reducing noise, fuel use, and harmful emissions. So they want to have less impact on the climate change, on the also the local air quality, and also the noise emissions around aircraft. So to be able to achieve these goals, you cannot just focus on optimizing the aircraft, but it is actually a very diverse, it's a multidisciplinary approach. You can look into new materials, new engines, alternative fuels, or the shape optimizations of the aircraft. But again, we need to consider about the entire system, not just the physical aircraft structures. So you need to consider how the whole operations. So that is what we call the real world engineering problems. Okay, so again, quickly, we look at how aircraft design process. So this is obviously before we had computing technology, before we actually relied on MDO. So these two photos, I took them from the appendix of the Raymer textbooks. So Raymer textbook is the holy grail of all aircraft design classes. But you can see that you can imagine that the Wright brothers did this to design their aircraft. Everything was pen and paper, back of the envelope calculations. And later on, we have wind tunnel experiments. Well, actually, the Wright brothers also did the wind tunnel experiments and the flying scales models. So these wind tunnel experiments and flying scale models can also help in the design process as well. Well, actually, obviously, they are better. They are better than just a pen and paper design process. And now we have been assisted with computational engineering, with the computer-aided engineering, or CAE. So first of all, well, even though we use CAE, we use computational models and mathematical modeling, it doesn't mean that we don't do experiments or flying scale models anymore. However, by using computational models, we can perform more design explorations. We can try different designs before we actually build the models to test in a wind tunnel or to test as a flying scale models. Because you can imagine that, you know, having actual physical models for testing can be expensive. In some ways can be dangerous as well, can be hazardous. So in some aspects, like for example, aircraft design, unfortunately, it is not something, it's not a field where you can test, you can come up with an idea, test your designs and see whether it crashed or not. You know, you don't want to do that. So that's why we rely on computer simulations. So that also means that the computer simulations that we have need to be able to be realistic, need to be able to really represent or the actual process. So this is the reason why you are taking this 3 weeks courses. And I also mentioned, you know, like we gave an example about the Comet, the window design change. So obviously we do not want to wait for another accident to drive design changes. So that's why we do simulations. So at least if it crashes in a simulation, it would not have any casualties. Okay, so a tale of two stealth aircraft. I guess you know what stealth means, right? So this basically means that the aircraft that are not detectable with minimum radar cross-section. So basically they don't want to be detected by the enemies. So these two aircraft, one is a Nighthawk, started in 1975. Then the other one is B-2 Spirit, started in 1979. Both of them are stealth aircraft. So what is the key difference in the aircraft shape? Did you see any? Oh, a lot of people answers. Sweep angle, detail. No, it's more general than that. Smoothness, smoother contour. Yes. So basically, if you see the Nighthawk, which is the left hand, which is the older one, the big brother, they have sharp edges. So it's basically constructed by flat surfaces. And then on the right-hand side, the B-2 Spirit, it has smooth surface, right? But I think some of you mentioned about the radar cross-sections, radar detectability. So obviously both of them were designed to minimize the radar cross-sections. But those of you have learned about aircraft designs or aerodynamic performance, so what will be the penalty of having flat surface? Yeah, so basically we talk about radar detection and the wave track. So in other words, the left-hand side would have worse aerodynamic performance. Okay, so basically, do you know what drove the design development from the big brother to the younger brother, from the flat surface to the smooth surface? So in other words, both of them are stealth aircraft. They could fly undetected. But if you look at the shape, the right-hand side will have better aerodynamic performance, which is always desirable. Materials operation ship detected. So what drove the design development? What enables the right-hand side to have smooth surface? Okay, actually the answer is computing power, because both of them were actually designed by optimizations. But in 75, when Nighthawk was designed, they could only model the radar cross sections of flat surfaces because of the limited computing power. So they could only optimize for flat surfaces. So for the B2 Spirit, which was started a few years later, the computing power already advanced. So they could start modeling 3D shapes, 3D surfaces, like curved surface. So they have the power, they had the computing power enough to model the curved surfaces. So basically, even when they designed the Nighthawk, they knew that this one didn't have a good aerodynamic performance, but that's the best they could do because of the limited computing power. But in the next generations, they can have a smoother surface. Okay, so any questions so far? So basically, those are only the introductions. But those, I think it is important for you to appreciate what you're going to learn in the next 3 weeks. And for some of the topics, I don't need to talk into details. I just need to give a sneak preview to make sure that you will attend the lecture later. Any questions so far? Or we should just continue. Okay, so modeling. So actually, when we talk about modeling, we don't only talk about mathematical models, because you saw that, you know, in the flying scale models, for the wind tunnel models, we also had a physical model. So when we talk about models, it could be mathematical, symbolic, or physical. For a mathematical model, for different problems, you will need to have a mathematical expressions. Okay, first, I will, there's a questions. Do you think there will be a completely automated MDO in the future? If you want to discuss about that, come back to my lecture on the 5th of August. So that's when we will talk about it. Okay, so you see the mathematical models. Here I only express y equals to fx, which is a very generic expressions of a mathematical model. It can be applied to anything. But what I want to tell you is that you will need to be able to have a mathematical representations of your system. So that also means that you have to be careful about the notations usage. So I see that some students, well, I'm not referring to you, but you know, some students, they might not be very familiar how to represent, you know, scalar factor matrix, because different things have different meanings. So this is just an advice for you. Be careful about the notations. Make sure that when you define the mathematical models, it is actually not only correct in terms of what it can model, but also in terms of readability by other people. So make sure the notations are correct. Is there only one model to represent a system? Anybody wants to answer? Is there only one model to represent a system? So you can use an example in aircraft design or in any of your topic. So yeah, depends on the assumptions. Okay, so basically the answer is no. There's not only one model to represent a system, because it really depends on what is your goal. So the different levels of complexity, different levels of computing powers that you have, different levels of resources that you have, whether you have to, whether you need to submit it tomorrow or next week, or you have to finish it in terms of thesis in 4 years, you know, you can still achieve something, but at different levels of fidelity. So obviously there's no one model to represent a system. And for example, in aircraft design, you have different stages, right? First, you start with conceptual, and then preliminary design stage, and then at the end, you have the detailed design stage. So in these 3 stages, you have a model to represent an aircraft, but they have different levels of fidelity. Because obviously, when you are at the conceptual design stage, you don't need to care about very detailed, you know, like you don't even need to do finite element analysis in the conceptual design stage. So that's you know, basically the level of complexity that you need, and also your computational budget your time budget as well. So that's how you decide. But when you define a model, it is important for you to know whether you will think about a system or a product. So again, that depends on what you want to achieve, right? So you need, by isolating a system, you have an imaginary control, a control volume. So by doing that, by having a system boundary, it will be easier for you to define the inputs and outputs of your model. Because again, at the end of the day, you need to represent y equals to fx. So you need to know what x are, what y are, and what are the functions. And since we're talking about real world engineering problems, so it is possible to have hierarchical models where you have different models for different subsystems. Well, actually, that is the realistic way to do it. You have different models to represent the structural performance of the aircraft, to represent the propulsion system, to represent the aerodynamic performance, and then you need to know how to combine them together. Okay, so again, as I mentioned before, you need to be very careful about notations. And I also want to emphasize that you also need to be careful about definitions. So if for people who are not experienced yet in modeling, computational modeling, I've seen that they mix up between variables, factors, and parameters. So factors and variables, they might mean the same things, but parameters are actually different from the others. So I think on this slide, even though for some of you it might be very straightforward, but I just want to have to make sure that all of us are on the same page in terms of definitions. First, variables. So variables define the different states of a system. So these variables include inputs and outputs. So in some modeling contexts, they also call this input factors and output factors. But actually, if you say input parameters, I don't think that is technically correct. Like if you just use it in discussion, I'm pretty sure everybody knows, everybody will get it. But technically, it is not correct. So variables or factors include inputs and outputs. System parameters are the quantities that are fixed in any particular model statement. So in other words, parameters actually define your model. So for example, if you have, if you select a certain material types for your part, then the material properties become the parameters. And so for example, if you want to evaluate the aerodynamic performance of a wing, a fixed wing. So for the wing, you have the geometrical parameters, and then you want to evaluate the aerodynamic performance at different flight conditions. So, so like the thickness and span, will it be variables or parameters? The geometrical definitions of the wing, will they be variables or parameters? Variables? No, actually it is parameters. Because the variables in this case, remember that I have a fixed wing. So the wing have certain geometry, span and thickness and chord length. And then I want to evaluate the aerodynamic performance at different flight conditions. So in this case, the geometrical definitions are the parameters, and the inputs will be the flow conditions. And the output will be the aerodynamic performance. Is that clear? Any questions? Yes. So basically, so again, it's okay if you are confused before I explain it, but once I explain it, I hope you are clear about this, and you can be consistent when you discuss with other people, when you discuss with your professors, and especially when you write papers. So it has to be consistent. Yes, Tim, I will get back to you after this. So system constants are easier. So because it's like gas constants or speed of light, you know, so those are the things that are defined by the phenomenon. And then the mathematical relations combine all three, all different stuff together. So yes, so answering Tim asked in the chat whether the whether the selections of variables and parameters depend on the problem. The answer is yes. So for example, the wing example that I gave you, the other option is you have a certain flight conditions. For example, this is the cruise conditions that the aircraft will fly mostly at, and then you want to evaluate, you want to optimize the aerodynamic performance. But in this case, you want to try different geometric parameters. You want to try different span length. You want to try different chord length. So in those cases, the geometry becomes geometry variables. And the flow conditions are fixed in this case, so they become the model parameters. So I think, yeah, so basically it is problem dependent, and so you need to really understand about what you are trying to design. Tim, I hope I answer you. Okay, thank you. Yeah, so again, design as a decision-making process. So this is actually, our transitions from talking about design modeling and then what you've been waiting for, which is the optimizations. So the concept of optimization comes about because essentially design is a decision-making process. If you are in aircraft design, maybe some of you, you know that even before we had computer programming, they will draw, people would draw the carpet plot. Are you familiar with that? So anyway, so it is more, it is very, carpet plot is a very primitive way to do optimizations. In other words, it was almost like trial and errors. But the concept of optimization always remains the same, that you always want to achieve a certain criteria. You want to select the best design based on the criteria or criterion that you set up for your design. So that is so basically optimization came from the fact that this design is a decision-making process. Okay, so in the decision-making, when you try to make decisions, you will, you will weigh between the pros and cons of every options, right? So I think, conceptually, you do it every day in your life. What do you want to eat for breakfast, for example? Whether you want something filling or whether you want something cheap, like you always have this kind of decision-making, and you always need to have the criteria. So in design as a decision-making process, we need to be able to have an abstractions or a model where you can modify the designs to evaluate the different alternatives. So for example, you need to have a model such that you can vary the geometry variables to be able to assess different wing shape options. And you also need a rational choice, which is the criterion in the design selections. Well, actually, in optimizations, we also talk criterion, which is singular, and criteria, which is plural. So optimization can have single objective or multiple objective, but it needs to have objectives. The criterion is not unique. So the same as previously, you can, your set of variables, parameters are not unique. It depends on the problem that you are facing, that you want to solve. The criterion is also not unique. So we will see, and well, I think you will actually learn in the next 3 weeks how to determine your, how to formulate your problems such that you can achieve what you want. So yeah, decision-making model. So basically, optimization model is a decision-making model. It needs to be to have an objective, and it needs to allow you to evaluate different design options, different performances of the different alternatives, such that you have a rational way to select the best design. So that will lead us to the optimizations. Yes. Any questions so far? Yeah, so this is just like one quote I like from Aristotle. That means from a long time ago. For the goal is not the last, but the best. So basically, even back then, they start thinking about how to get the best, even without computers. Okay, So optimization is a more complex way of performing design. So essentially, designing something does not always involve optimizations. So for example, if you design a chair, it might be quite simple, right? Like especially, okay, let's say you design a stool. So the requirement will be easier, and you might not even need to do optimizations, because what you need to achieve is make sure the stool is strong enough to carry the weight of the expected payload, whether it's a kid or adult. So there's only one goal in that. So how to recognize the kind of problems, the kind of real world problems where optimizations will be suitable or will be required. So essentially, you will see whether there's a design compromise, whether there's a whether when you try to improve the performance of a discipline or a subsystem, whether it will sacrifice the performance of other subsystem. Okay, there's a questions, but I think I will leave it to later. Yeah. At the end of the lecture, you can come back to me whether it is answered or not during the lecture. So back to the optimizations. Yeah, so basically we look at the design compromise. If everything goes in the same directions, if you use stronger material, you will have a stronger product. So that doesn't require an optimizations. But if improving one will sacrifice the other, that's when you actually need an optimizations. So some examples again in aircraft designs, but feel free to give examples in your more specific topics. Aero and propulsions. So the aerodynamics concerned with how the fluid flows on the structures, and that will the same flow will also be related to the inlets of the engine or the propulsion systems. So these two groups might actually have different priority. Aero and structures. So the structures would always want to make the shape as sturdy as possible, but the aero group will try to make it as lean as possible. So these two again, are contradicting each other. So that's when an optimization is required. So essentially, design might not have a unique answer. So even in my aircraft design class, if I have the same design project for every groups, none of the group will come up with the same answer or with the same aircraft. So when we talk about design, we always talk about the balance. And when we talk about balance, we actually look beyond the technical aspect of it. It's not only we don't only consider the engineering elements of the product or of the design process, but like their economic factor, political factor, schedule, environmental. So all this, even in some cases, is the business factor, the competitiveness between the duopoly, and so basically a lot of things are driving the design, and we as engineers, we need to be able to put things together. So that's why in designing something, it's not only um, a single step, but it will require multiple steps. So I think I mentioned a few slides ago that since the 1960s, the key players for aircraft designs were not only the aircraft designers or the aircraft engineers, but also the cost engineers as well as the manufacturing team. Which factor to prioritize? So this also change over time. So for example, at the beginning, they just want something to fly, and then something to fly that is cost effective, and then something to fly that is, cost effective and environmentally friendly. So and with a higher capacity. So basically, which factor to prioritize, it changed over time, and that is very challenging because if you think about it, in aircraft design, the whole design process, even just changing the variant of aircraft design, can take up to 10 years or even more. And a lot of things change. A lot of things would change, right? The government policy might change. There might be new environmental considerations that needs to be included in the design process in those 10 years. But when we start the design process, even though we try to include everything, it is not possible to model everything. So this is actually will lead you to the optimization under uncertainty lecture. So how can you optimize something? How can you try to design something that is robust despite the potential changes in the requirements? So this will lead to why you need to learn optimization under uncertainty. So essentially, there are three key questions key questions in design optimizations. How do we describe different design alternatives? So again, this is what we have discussed before. We use mathematical models, but the mathematical models, you have to make sure that it will enable you to modify a few parameters to evaluate different designs. So I believe this will be further discussed in the advanced modeling and simulations in engineering design by Professor Lafi Zuhal. What is our criterion for best design? So this is essentially the objective function to be maximized or minimized. Or what are the goals or the criteria that you want to achieve with your design? And lastly, what are the available means? So this refers to the set of requirements or constraints that must be satisfied by any feasible or acceptable design. So these are the three key questions that you need to think about before you actually start formulating your optimization problems. So the design process, first, obviously, the recognition of need. You need to know why you have to do this. For some cases, it's because your professor asked you to, it's because you need to complete the assignment, but that's how everybody started, right? And then, okay, so once you know why you need to do this, what kind of objective you want to achieve, then you start with the problem definitions or the technical statement of the problem. I think I will get back to this later. And then you need the synthesis, which is the creation of the physical configurations. So first you have the abstractions. Oh, I need to have a model that can evaluate the aerodynamic performance of the aircraft. At the same time, it will enable me to evaluate the structural performance, the maximum strength criteria of the materials or something like that. So those are, so you need to, and then once you have the abstractions, then you need to be able to model it. And then analysis, you need to be able to evaluate the performance using engineering science. So this is where the programming will come into place as well. And lastly, the optimizations. So typically we don't do optimization manually. So there are some algorithms that can help you to find the minimum or the maximum. But you need to understand all this, all these 5 steps to be able to achieve what you want. So that also says that if you want to study engineering nowadays, there's no way you can skip programming. So if you're not yet familiar with programming, you should come to the tutorial 0 tonight. So this is another promotions. But if you haven't been familiar with programming, please come. Even if you are not familiar with Python, even if you prefer MATLAB. But based on my experience, and I'm pretty sure your other professors and presenters will agree with me that once you learn one programming language, the knowledge is actually transferable to learn other programming language. So even if you use Python and actually for your work you need to use MATLAB or Julia or other programming language, it doesn't matter, because what is important is to get used to the programming thinking. So that is very important. And if you want to stay in aerospace engineering or other type of engineering, and if you want to do research, then you better start tonight. Okay, so this is a more formal definitions of optimizations for design. We start using the terms that the optimization MDO community will use. Essentially, optimization is a systematic method to achieve the best possible results under given circumstances by varying design variables. So they are color coded. I don't know whether you can see the blue corresponds with the blue, the green corresponds with the green, and the red corresponds with the red. So essentially in the optimization for designs, actually I saw some of the comments at the beginning of these lectures. It seems like some of the participants are already familiar with the concept of design variables, of objective functions and constraints. So these are just like the formal definitions. So the design variables refer to those variables that we can vary. And the selection of design variables also need to be done carefully. They should be as independent as each other. Because if they are not independent as each other, you know, like the optimization algorithm and the mathematics will get messed up. The objective functions is what do we want to achieve? Again, we can talk about single objective or multi-objective problem. So essentially, it is a measure of goodness, but it needs to be able to express mathematically or numerically. Constraints are what are the circumstances or what are the requirements that you need to meet. So in other words, these constraints will define the feasible design space in your design process. So for example, typical aircraft design is you want to vary the aircraft wing parameter, the aircraft wing variables to maximize the aerodynamic performance, or you try to minimize the fuel consumptions, or you try to minimize the aircraft weight. At the same time, you have to make sure that the structures will not break mid-flight. So you can put the stress concentrations as one of the constraints. So this is just how you frame your problems into optimization problem formulations. But obviously, it will be further discussed there's a lecture for optimization problem formulation. I believe it will be your second lecture. Okay, so actually, an everything optimization is neither feasible nor desirable. So what it means is that we cannot be too greedy, or we cannot just think about, oh, I want to create an optimization problem or solve an optimization problem that is as complete as possible, as realistic as possible. So I want to model everything. So that's not a really good approach, because as you increase the complexity, it will also require higher computational resources and computational time. So essentially, as you include more design parameters or design variables, or if you include more detailed in the design, you will need to have more computational resources. So at some point, you will see that it is actually the required computational resources increase exponentially. So it's not possible to include everything. And it's also not desirable, because in some cases, you know, adding more design variables will not matter as much anyway. So why is that so? We will see in the next few slides. Yeah, so guides for designers. First, I think the bottom line is you need to have a very strong domain knowledge. You need to be first and foremost be familiar with what the problem that you want to optimize, and then you know about what methods you can use, and you try to put things together. So again, first, the optimization problem formulations needs to be as realistic as possible while considering the computational budget. So it doesn't make sense if you try to design something that is as complete as possible, but there's no way you can finish it, right? And then include design variables that really matter. So, the objective function might be insensitive to some variables. In other words, if you vary some variables, it will not change the performance anyway. So why do you need to do that? Include sufficient constraints. And so basically, you need to make sure that the design space, based on the constraints that you specify, you will have feasible regions. You need to have feasible design space. So yeah, so I believe this will be discussed more in the optimization problem formulation lecture. But remember that you need to make something that is solvable. Okay, so again, in terms of history, I'm not going to discuss in details. This is just to give you, again, an overview, a historical perspective. So actually, if we talk about optimization, the first thing that enabled optimization was the development of calculus. So you already know, all the names that I mentioned here, all the mathematicians that I mentioned here. So you're already familiar with that, with the names. But basically, it started with calculus. In a way, calculus enables us to do optimizations. And calculus will appear in sensitivity analysis, design under uncertainty, and gradient-based techniques. So if you want to know more about it, attend the lectures. And yeah, so the other one that helps is the response surface method. Okay, so there's a questions about the computational budget. So I just give a brief overview. So basically, computational budget refers to the computing powers that you have, whether you only have your desktop computers or whether you have you have access to supercomputing. So that will, that will determine what kind of analysis you can run. Like if you only have your laptop, then it's almost impossible to perform the whole RANS, like very high fidelity aerodynamic modeling. And the other one is also computational time. Again, whether you have to submit it tomorrow or next week or at the end of your thesis in 4 years. So that's basically what you have. Yeah, so response surface method, we are going to revisit this in the surrogate modeling. So response surface, even though this looks simple, but it actually really helps optimization development. And multi-objective optimization, the Pareto optimality. So you will discuss this more in the multi-objective optimization lecture. And I think these are just very brief introductions. Linear programming, I think simplex model was, if you learn about optimization, this was the first thing you learn. But actually people don't use it anymore because real world problems are non-linear. So linear programming does not really apply. But understanding the basic really helps you to understand the more complex methods. And then we also have the KKT conditions, which is basically the optimality condition. So I'm pretty sure it will be discussed later as well. Yeah, so this is basically how we express the design problem as a numerical optimization problem. Some of you might already be familiar with it. So if you see on the right-hand side column, we have the objective functions, design variables, and constraints, and also the variable bounds. So the constraints can be inequality or equality. But what you see in the middle, so basically for different functions, you will need to have a mathematical expressions for the objective functions as well as for constraints. So these are where the mathematical modeling come into place. And later when we do the approximation tools that Pram will discuss 2 weeks from now, so that can be used to represent the objective functions, to represent the constraints. So this is how everything comes together. Numerical optimization algorithms, gradient-based algorithms depend on gradients. They use gradient informations. And we also have the gradient-free algorithms. Again, you will have a lecture each to discuss about gradient-based as well as the evolutionary algorithm. But this is just to introduce to you, especially if you haven't been familiar with it. So be careful when we have informations about minima or maxima. They can be local, global, or weak local minimum. So which one will be sufficient for you? It will depend on your problem. It will depend on what you need. And it depends on you as a designer. In some cases, local minimum is okay. In some cases, you have to find a global minimum. So the selections of gradient-based methods or the gradient-free methods will determine what you can get. So I will leave it to the actual lectures later on. So this is just a sneak preview. If you're curious, don't skip a lecture. So optimization in aircraft design. Again, this is just introductions. So in aircraft design, I think the idea of optimizations started because the developments of CFD, which is computational fluid dynamics, and CSM, computational structural mechanics. So basically, they have the CFD and CSM to help analyze the aerodynamic performance of the aircraft as well as the structural performance of the aircraft. And then in the starting in the 70s, these two methods were combined with the gradient-based optimization with constraint optimizations to have aircraft design optimizations. The common objective functions, maximize the aerodynamic performance, minimize the direct operating costs, fuel burn, and then nowadays we start including the noise emissions as well. So again, the objective function will depend on what you want to achieve. MDO is, I think if we talk about optimizations, MDO is definitely the current state of the art, because if you talk about real world problems, everything is multidisciplinary. And that's also why we have this, this program. So stay tuned for the whole 3 weeks. So when we talk about MDO, essentially, we don't look at different subsystems as a single disciplinary problem. But after we do, having been able to analyze the different disciplines separately, the next question is how to combine them together such that you can actually account for the interdisciplinary coupling between the different disciplines. So one that is very commonly performed, and I'm pretty sure this is what Nathalie Bartoli will also discuss, is the aerostructural optimization of the aircraft. So this of the aircraft wing. So this is like the starting point of MDO applications in aircraft design. So MDO has been shown to be effective not only in designing conventional aircraft, but also unconventional aircraft configurations. So for example, double bubble, blended wing body. So the references are given here. So note that if we design a conventional aircraft, we have reference data that we can look upon. But if you are trying to design something completely new, for example, the double bubble or the blended wing body, you need to be able to simulate the whole thing anew. So that's where MDO really plays a part. Okay, so again, this is just to make sure that you will not skip any lectures on optimizations, because if you think about it, all the important parts will be covered in this 3 weeks of lecture. Okay, sensitivity analysis. So anybody wants to say, what is sensitivity analysis? Or what do you need? What do you know about sensitivity analysis? Come on, say something. Even if it is wrong, at least I will see your name. The sensitive. Yeah, so basically when we talk about sensitivity analysis, first, it's not only about the objective function with respect to the design variables or the inputs. If we talk about sensitivity analysis, essentially we see how the change in inputs lead to the change in the output. Yeah, so let's see. So some of you talk about uncertainty, so that also applies. You will see in the next few slides which variation affect the most change on the output. That is actually a very good point. So which we will see shortly. Yeah, first, I'm sorry if I cannot address all the questions, but I saw that, like all of you have the correct answers or correct concepts. But actually, most of you just cover bits and pieces. Like, for example, some of you talk about local sensitivity analysis, and some of you talk about global sensitivity analysis. Yes, so basically, you're all correct. So actually, when we talk about sensitivity analysis, a lot of people think about gradients. Do you? Did you think about gradients when we talk about sensitivity analysis? Is gradient a measure of sensitivity? Yes. Yes, so gradient is essentially a measure of sensitivity, because a gradient, you think about how one variable will change with the change of other variable. However, it is only a subset of sensitivity. I think some of you have correctly identified that this is gradient is a means of measuring sensitivity, but it's not all. And so basically, the general idea of sensitivity analysis is to investigate how the change in input factors affect the change or the variability in the model outputs. And we have two types of sensitivity analysis. So this is something that you need to be to make sure that conceptually you are correct. One is the local sensitivity analysis, and the other one is the global sensitivity analysis. So local sensitivity analysis is evaluated at one single point. Global sensitivity analysis, we actually look at the variations of inputs and also the variations in the outputs in the entire design space. So the question now is gradient LSA or GSA? I think I asked more questions than students asking me. Yes, LSA. So that is correct. So basically, gradient is a form of sensitivity analysis, but only at the local point. So we will talk about the GSA, or at least a brief introductions later. First, I'm not going to cover everything, but for a GSA, which I understand that is not, some of you might not be familiar with the GSA. Actually, I put a lot of references. So for LSA, it's easier to understand because it's, like if you look at the delta fx divided by delta x, if you change the input x, how will the output fx change? So that is, in a way, is close to gradients, right? So derivatives or gradients are sensitivity taken for infinitesimal steps. So I think this much you should know, like you should learn before, maybe even in high school. So this concept is pretty straightforward. Okay, so I saw that some of you mentioned about the partial derivatives. So yes, that is correct. Can I actually try to? Okay, I just muted somebody. Okay. So in this illustrations, I think you can see how we can use sensitivity analysis or the derivative informations in an optimizations. So essentially, if you look at the partial derivative, it will see how the function change, the output function change with the change in the input, like either in the x directions or in the y directions. And the sensitivity informations can also tell you whether it is your minimum or maximum. So basically the optimum. So what is the conditions to find an optimum point? I know this is very easy, but I just want to make sure that you are still following my lecture. It's already almost 1.5 hours. So what is the conditions? What is the gradient value at the optimum point? At the maximum or minimum? Okay, at least I know you're still awake. 0, yes. Yeah, so basically that's how we use sensitivity informations or the gradient informations. But remember that gradient information is only a local sensitivity analysis. Yeah, so one of you already mentions that we use sensitivity informations also in uncertainty analysis, uncertainty quantifications. And I believe when you do the robust optimization or optimization under uncertainty, this information is used a lot as well. And the risk assessment. So for example, if we have hypothetical questions, if the airline wants Delta X more passengers, then what will happen? Do we need to change the design? Will the designs that we have now still work for the new demands? And of course, optimizations. Yeah, so basically, I think, all of you have answered correctly that at the optimum point, you have the gradients equal to 0. And the other thing is, if you know, yeah, so if you know the gradients at different points, so you know which one is the directions, the steepest descent directions, or in other words, by knowing the sensitivity informations, you will know what is the directions, the best direction for you to go to find for your optimum. Okay, can Monte Carlo give this gradient? So, well, actually, Monte Carlo can do a lot of things, but I don't think you need Monte Carlo to do this gradient informations. Actually, there are a few methods to calculate sensitivity, so you don't really need to resolve the Monte Carlo, even though I'm pretty sure it can help you. But yeah, technically Monte Carlo can help, but it's not needed. Can a saddle point be an optimal solutions? It really depends on you, but in general, no. In general, you try to find a true optimum and the true maximum or minimum. Yes. So again, the text in red are where you are going to see this sensitivity more in the lectures. Okay, since we talk about designs, so what do you need to do as a designers and how can you make use of the sensitivity informations? So first, as a designer, in addition to find your design variables that achieve your objective, you also need to know the sensitivity informations. So for example, how will the objective or the performance change when there are change in requirements, when there are change in measure of merits or program strategy or any other parts of the design. So essentially, performance sensitivity means we need to quantify the deviations from design conditions affect how the deviations in the design conditions affect the performance. It might be easier to talk in terms of examples. So for example, how do high altitude and hot temperature affects the takeoff distance? So again, this is an aircraft example. Okay, let me see. The second one makes more sense. How much fuel can be saved for every kilogram removed from the structures? Because we know that if the aircraft structure is lighter, then the aircraft will require less fuel to fly. And when you change the cruise altitude or the altitude at which the aircraft is flying for most of the operations, if you change that, the aerodynamic performance will also change. So how will it affect the range or how will it affect the fuel performance? So the question is, which one will have a higher marketing advantage, less sensitive or more sensitive? Answers, please. Less sensitive. Yeah, so that is correct. Because if your design is very sensitive to the requirements, that means if all the project finished 10 years after, something changed, you might risk your aircraft will not be able to be produced, which unfortunately happened before. I think you can check the Lockheed TriStar L1011. So that's one of the example that once they finish the design, the whole designs, and then the market requirements or market demands change, and they were very sensitive to those requirements. But if you, yeah, A380 is one of them. Thanks, Tim. So basically, but if it is less sensitive, in other words, if the requirements change, your aircraft can still perform or your product can still perform to a reasonable degree, or it might require some minor changes which you can afford. So yeah, so less sensitive is better. So again, robust optimization. Okay, so you already got the idea about sensitivity analysis, how we can perform trade-off analysis for a better informed decision making. So remember that the optimization design is all about decision making. So I think what I want to emphasize here is that, you know, let's say you're working on a project, you want to design a super jumbo aircraft. So the first, the first person who came might be your customer, and they have a lot of requirements, right? So after you do your design and analysis, you need to be able to inform the customers about the options. So even though the customer gives you the requirements, doesn't mean that you have to say yes to everything. So a good designer will get back to the customers and say, oh, if you relax these requirements a bit, you will gain in terms of, is better noise emissions or less fuel consumptions. It will be more environmentally friendly, but you sacrifice 10 passengers, you sacrifice 10 payloads. So all this needs to be communicated back to the customers such that they can make a better informed decision making. So they know the pros and cons of different options. And to achieve that, the trade-off analysis based on sensitivity analysis is very important. Okay, so now global sensitivity analysis, which some of you might not be as familiar as the local sensitivity analysis. Again, we won't have time to go into details, but I provide some references for you to look further into. So in global sensitivity analysis, it tries to quantify the contributions of uncertainty in each input factor to the output variance. So as you can see in these illustrations, let's say the blue circle is a total variance. And after performing the global sensitivity analysis, you can you can segmentize, you can get a pie chart to see the contribution for factor 1, factor 2, as well as the interactions. And in GSA, we have the main effect sensitivity analysis and total effect sensitivity analysis. So one of you mentions or asked about the design space, like whether it has a system boundary. And yes, for global sensitivity analysis, you need to define the range, the value range of the different inputs. In other words, you still need to define your system boundary for you to be able to quantify the contributions. How can GSA results help the design process? The two key purposes are, first is the factor prioritizations. So basically, imagine you perform GSA, and from here you can see factor 1 will have higher contributions to the total variance, right? So if you want to minimize the output variance, the first thing that you want to reduce is factor 1. Because if you try to reduce factor 1, the uncertainty of factor 1, then you can reduce more of the output variance. And once you know which factor is more dominant, then you can allocate your research priorities to better understand about the factors. But of course, you have to have an understanding of aleatory uncertainty and epistemic uncertainty. So do you know aleatory and epistemic? Okay, so first their question is PCA part of GSA? I think PCA is more on the surrogate modeling. And okay, so aleatory uncertainty and epistemic uncertainty. So epistemic uncertainty, okay, aleatory is simpler. Aleatory uncertainty is based on the system randomness. So for example, the weather situation, if you're in Hong Kong, you know how unpredictable the weather conditions this week, suddenly a thunderstorm. So, so essentially when we talk about aleatory uncertainty, they are completely random, like the wind speed variations, it's a natural phenomena. You cannot really change that. But epistemic uncertainty is due to lack of knowledge. So for example, if you have low fidelity model, it only has a certain capability to explain about the phenomena. But if you have a higher fidelity model, then it can model the phenomena better, and you can have a better representations of the uncertainty. So essentially, aleatory is based on randomness, and epistemic is based on lack of knowledge. So the factor prioritization applies to which one? I think KL is more other expressions. It's not really aleatory or epistemic. Like, for example, normal distributions can be used to determine aleatory or epistemic. So the answer is actually epistemic only, because if you, for factor prioritization, it is true that, let's say factor 1 is an aleatory, like the factor 1 is Wien effect. So, but this is something that you cannot really control. But if it is epistemic, like, for example, if you have a better model to represent the propulsion system of the aircraft, you can better predict the fuel flow variations or something, then that can be improved by the factor prioritizations. But essentially, when we talk about aleatory, even if we know that it affects a lot, but if there's nothing we can do about it because it is part of natural randomness, there's not much we can do. Okay, so factor fixing is we can pick the factors that have little contributions and just fix it in the model, so it will simplify the model. Okay, yeah. So these are some methods and references for GSA, so for your own reading. Okay, so we need to talk about the surrogate models and machine learning, and I'll try to finish it in 10 minutes. But actually, in this presentations, some of you already have a lot of questions, so we don't need to have like the whole 20 minutes for questions and answers. So I think by now you know why we need surrogate models. So surrogate models are essentially approximation models. We have looked into sensitivity analysis, optimization, uncertainty quantifications. And some of these methods for sensitivity analysis, uncertainty quantifications, Monte Carlo simulations can be used a lot. So that means that this analysis require a large number of simulation runs. And in some cases, for example, a high fidelity CFD analysis to evaluate aerodynamic performance, ideally it can take use supercomputing, parallel computing, and it might still take few hours or even few days to run. So if you need to do uncertainty quantifications on optimization using those high fidelity models, it can be computationally prohibitive. So that's where surrogate models come into place, where they are used to replace the original computer simulations to perform the above mentioned expensive analysis. So essentially, surrogate models are approximation models such that they are simpler, cheaper, and much faster to evaluate. Again, for me, definitions is very important. So the classifications, this is a classical classifications. Surrogate modeling techniques can be divided into physics-based model and black box or data fit models. I think most of us are more familiar with the black box models. But physics-based model, the key differences is that in physics-based approach, you need to know the governing equations of the system. So it is they are called the intrusive methods. So either the reduced order models. So this is where the PCA comes into place. And there's a very good question. Is surrogate model different with a lower fidelity model? Technically, lower fidelity model actually belongs to the physics-based approach, which is the hierarchical models. So technically, if we talk about surrogate models in general, by definitions, if we have a CFD analysis and if we want to run it with coarser grid or more relaxed convergence criteria, so in other words, they are actually can be considered as a lower fidelity models. Technically, they belong to the category of surrogate models. So these two, reduced order models and hierarchical models, you need to have access to the governing equations. The data fit surrogate models or the black box models are non-intrusive methods. And they are essentially by using samples. So you can generate the models if you have a set of the inputs and a set of the outputs of the functions that you want to represent. So in other words, you don't really need to know the governing equations. That's why it's called a black box. As long as you have the inputs and outputs, you can derive appropriate surrogate models. So I'm pretty sure most of you are already familiar with these models. So there are three components. First is the design of experiments or sampling, model structure selections and parameter and hyperparameter estimations, and model assessment. So that includes the verifications and validations. Okay, so these are the actual classifications of black box surrogate models. They can be classified based on data points, parameters, and derivation techniques. So I'm not going to explain one by one. If you have questions, feel free to either email me or try to find my PhD thesis. I explain everything there. But if you email me, I'll be happy to answer as well. So again, but definition is important. You will see that by the derivation techniques, we can have either regression types or interpolation types. So they are very different. Regressions, essentially, the data involved or the sample data involved will have random errors. The interpolations, the derived models will go through every sample. So I think by looking at these two illustrations, it's kind of clear that the regression is suitable for measurement data where randomness exists, and interpolations is more for deterministic computer experiments. Yeah, so issues, limitations with surrogate modelings. So remember that we need to derive model parameters, and usually we derive the model parameters based on the observations. So the one set of model parameters need to be able to represent the whole design space. So first, when there's a heterogeneity in function profiles. So for example, if the function profiles, one side is quadratic, the other side is linear, it's kind of obvious that it will be difficult to find one model that can fit both profiles. Surrogate models' curse of dimensionality is the typical problem faced by everybody doing research in surrogate models. So basically, the capability of surrogate models are still very limited. I'm pretty sure it will be discussed in the lecture later on. So there are ways to advance surrogate modeling methodologies using gradient informations, active learning approach, multi-fidelity modeling, and also by implementing machine learning techniques. There are some research to use more than one surrogate models, and typically they're used by combinations or selections. So to address some of the issues that I mentioned earlier, this can also be options. Okay, so what can we use surrogate models for? So I'm not going to discuss in details. I think this will be for your own reading. This is just 2 slides. But I think what is more relevant for our discussions in these 3 weeks are to provide the curve fit and response surface to represent the expensive computer simulations, such that you can perform optimization, uncertainty quantification, and sensitivity analysis in reasonable time. So the highlights are the 2 key requirements. It needs to have significant increase in speed as well as useful accuracy. So I guess that makes sense. Okay, so this will be the last part. A lot of people ask whether surrogate models and machine learning, are they the same, or do they belong to the same category? So to answer it, just listen to, it is more complex than that. But essentially, surrogate models is, some of the surrogate modeling techniques can be considered as the statistical machine learning. Statistical machine learning's the main goal is to develop algorithms that can learn from data, so the patterns or hidden patterns in the data, to construct stochastic models. And these stochastic models can also be used to represent the system. So this is where the concept is similar to surrogate modeling, but of course only with this black box surrogate models, which rely on data. The types of learning, we have supervised learning, unsupervised learning, reinforcement learning, and semi-supervised learning. And again, the details, I think you can look at them by yourself. We will only look into the first two, but I believe in these 3 weeks, you will also discuss about the deep learning. And I'm not sure what Pram will cover in his lecture, but the main difference between unsupervised learning and supervised learning is that in unsupervised learning, you don't have any category. You just have a bunch of data and you try to find hidden structures in the data, or you try to recognize some patterns in the data. So it is more difficult than supervised learning. In supervised learning, you have the outputs. So in unsupervised learning, you only have X, which are the inputs. But in supervised learning, you know the outputs. So it is easier to do the modeling. So in supervised learning, we have classifications and regressions. So classifications, the outputs will be labels. The data can be labeled to different categories. And for regressions, the target outputs are continuous. So the regressions that we talk here is similar to the regressions when we talk about surrogate modeling techniques. So in a way, if to draw the lines between surrogate models and approximation models, black box surrogate modeling can be seen as a special case of supervised machine learning applied in the engineering design practice. And I'm pretty sure Pram will also cover this in his lecture. So again, these are the relevant lecture topics for surrogate modeling and machine learning, which you will learn in the next few weeks. Final remarks. I think what I want to emphasize here is that in the next 3 weeks, you will learn about different methods, different techniques, but they will be useless if you don't have a strong domain knowledge. So how to make your knowledge useful is you also need to have a strong domain knowledge. You need to formulate the optimization problem that is realistic. So what happened when you know the techniques, but without a strong domain knowledge? So for example, you can formulate an optimization problem without any visible design spaces or an invisible initial point to start an optimizations or data analytics results. Like after you do the machine learnings and the findings will give you something that is obvious, that you don't even need machine learnings to tell you the patterns. So all this, I think what are important for you to think about as engineering, as engineers, as researchers. Yeah, so based on my experience, as I mentioned, I did my PhD in aircraft design, MDO. Even to perform the optimization, sometimes you need to start from mini optimizations. So different levels of optimization until you can actually formulate the final problems. So in other words, even to define the constraints, to find the initial point, sometimes you need to do a series of optimizations, and that is quite common. So, but in this 3 weeks, you will also have the opportunities to listen about real-world applications. So here are the list of the speakers, and Professor Joaquim Martins is my PhD advisor. So I think you will see a lot of parallels between his ideas of MDO and what I've mentioned to you today as well. Yeah, that's all. I think I really hit the mark, like 5:50 Hong Kong time. If you really have to go, you can go. But if you have like last minute questions, I'll be happy to entertain some questions.
Okay, thank you, Dr. Rhea, for your great presentation. We will very delight for us to have the overview of this course. Okay, and I think there are some questions here in the chat box. do you want me to read it for you or?
No, I think I can
Okay.
just address some of the more. Okay, so okay, so first there's a questions about the key or main difference between surrogate and machine learning. I would let Professor Pramudita Satria Palar to cover it in his lecture.
Yeah,
Because if
just call
I
me Pram.
yeah, so Pram, he's much younger than me anyway. Yeah, so Pram will cover it, and he will be very excited to talk about it. So I'm not going to cover it. So you have to attend his lecture. He's cool, by the way, and he will deliver a really nice lecture. Yeah, so that will be addressed in his lecture. And oh, somebody says just the first day. I thought she would say, but I'm already exhausted. But luckily she didn't say that. How can we trust our stat-based black box surrogate models if we have a highly nonlinear and probably discontinuous system? First, read my paper. No, I'm kidding. But to be honest, I did address that in one of my paper. But this is a common problem. So if you recall, when I talk about surrogate models, the two key requirements is that it needs to reduce the computational costs, and second, it needs to have a good accuracy. So how to ensure that we have good accuracy? There are several ways to validate the models, and it is a must-do step before you can use the surrogate models on any applications. Again, Pram will cover it. I'm not going to steal his limelight. But it's a really great questions because most of the problems will be highly nonlinear. Some are discontinuous. So for that part, you can read my paper. Actually, I did mention in one of the slides is the mixture of experts thing. And ooh, seems like you are still, the first lecture didn't scare you off. Unsupervised learning, again, I think this will be the territory of Pram in his lecture. But I think just because unsupervised learning exists doesn't mean that we always have to use it. To be honest, if you really work on design optimizations, most of the times we will only do supervised learning. But of course, the unsupervised learning, okay, this can be a bit complicated. It can be in, I would say this, unsupervised learning can be involved in the design process and in the design optimization process. But I don't think it will be in a conventional method. So I don't think you will use unsupervised learning to represent the objective functions. It can be part of how the objective functions is defined, or it can be part of how the design space is defined. And one more advice that I will give to all of you is that is the principle of parsimony. Do you know what it is? Principle of parsimony. So basically, you don't complicate your life. So principle of parsimony means you go for the simplest option. So for example, if you actually, I discuss it in my paper as well. So in one of my paper, I discuss about mixture of experts. Do we actually need to use multiple surrogate models for to represent a function profile? So by applying principal parsimony, the conclusion is that if the problem is simple enough, then you use something that is really simple. Like for example, if polynomial regression can work, why do you need to use Gaussian process? But so this is why I say you need to have a strong domain knowledge. You don't try to model a quadratic function with something more complex. Yeah, Occam razor. So that's another expressions. I think Danny Go mentioned it in the chat. So yeah, so that Occam razor and principle of parsimony basically talk about the same thing. Don't complicate your life. Once you get older, you will appreciate that more. Yeah, so it's the applied version of Occam's razor. Empirical to use unsupervised learning or other. What do you mean by that? Okay, let's 1 minute. So again, so the guidelines is that try to be as simple as possible. So you need to find exactly the, okay, so if we talk about it that way, just to find the right model is an optimization, right? You want something to optimize your accuracy with limited budget. So the computational time is a constraint. Empirical, so somebody mentions about empirical model. So empirical model is basically referring to modeling based on data. So in a way, surrogate models are empirical model. So that I think when we talk about empirical, it is the difference, or it is as opposed to physics-based model. So physics-based model, typically it is characterized by the fact that we need to know the governing equations of the system. Like for CFD, you need to know the PDE equations on how to express the Euler's equations, the Rand's equations. So that those are physics-based model, but empirical model will be based on data. So I guess I hope that explains. So okay, so somebody says that the supervisor asked to use unsupervised. To be honest, there's nothing wrong with trying to push the boundary, but first, don't use it for the sake of publications. There will be ways to use unsupervised learning in deriving surrogate models or in solving optimization problems. Actually, there are papers on that. There are already papers on, some groups actually use unsupervised learning to define the design space of the airfoil ship. So what I'm saying is that um, there are ways to use unsupervised learning effectively in your design optimizations or in your surrogate models constructions. But what you need to think about is that don't force it, because if you force it, the value will be limited. So I always advise my students, don't do something for the sake of publications. Do something to introduce new values to your research field. Uh, 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 uh. Oh, they're in. Okay, so basically, because this is almost the end of the period, if you have to leave, I'll be happy to answer some of the questions unless Nathan or Pram kick me out. So before you kick me out, I will still answer some questions. So I think you, Faiz Izzatur Rahman, mentions that, with a lot of discontinuity, non-linearity in the problem, Kriging PC model will be redundant in surrogate models. This guy needs to read my paper too. So basically, you really bring up a really important point, because and I think I will cover this on 5th of August, on the last day of your program. So you are right that there are already some fancy methods, but in most cases, they are insufficient, because again, people try um, to model higher and higher level of complexity. So um, so that's why research, even though Kriging PCE are already very well established, but there are still growing numbers of papers in even in those topics. And to be honest, Pram is one of, like Pram and Professor Laffy, they lead some research to keep advancing the methods. That is precisely to answer your questions. More sophisticated method, I think they will be under development, and most of the times it will be combinations of methods. That will be my personal point of view. And of course, it is possible that new methods will be derived. Okay, so there's some questions about physics-based surrogate models. So essentially, when we use surrogate models for objective functions, it can be anything. So it can be physics-based model. it can be, I mean, physics-based surrogate models like low fidelity models, or principal component analysis, PCA, or it's based on physical. Okay, let me read this again. A physics-based model is used to estimate. So I think in your case, Franco, it just means that you represent your objective function with using lower fidelity model. I hope I answer your questions, but feel free to ask again. Where can I read more on the above mentioned types of models? Which models do you mean? Hold on. Okay, I think somebody mentions about engineers. Engineers need to be mathematicians. Actually, you know, I'm teaching undergraduate in aerospace engineering at HKUST, and that's the first thing I always tell them. If you want to study aerospace engineering, to actually work in this field, to do research in this field, two things that you cannot escape from are mathematics and programming. So no matter what you do, you still need to have these two skills. And even if you go to NASA, Boeing, Airbus, they will look for these skills particularly. Yeah, so I think, Franco, I hope I answer your questions, but if I haven't, feel free to send me an email or whatever, or you can also contact Nathan and he will help connect you with me. Okay. Yeah, so, but I hope you will get a rough idea. But what is more important is that you have to attend every lecture, because I think by the end of this 3 weeks summer course, when I see you on the 5th of August, you might not have any more questions because you get more informations from the other experts. They are actually really experts, I can tell you that. I think I saw somebody that I know. Pak Heru, is that you? Pak Heru from Lapan. Anyway, thank you everyone. I'm sorry I took more time.
Hi Rhea, this is me, yes.
Hi. Yeah, it's been a while since
Glad
the
to
last
see you again.
class. Yeah. Okay.
I think all of the questions are answered well.
There's one question. I think, sorry. Hyperparameters in Kriging's considered as system variables or system parameters. I think hyperparameters will be properties of the models. So it will be, it's considered as the model structure of the surrogate models actually. So they are actually system parameters, I would say, yeah. But if you have further questions, contact me or contact Nathan and he will help you find me. Yes. Okay, I'm not going to answer any more questions. So Nathan can say the last word.
Okay, so thank you for your lecture, Dr. Rhea, and I hope this will be fun for all of us and useful for our knowledge also. And for you to be informed, please don't forget to fill out the attendance form so that we can know your attendance. Maybe I'll send you once more the link.
And I also put my email address.
Yeah, that will be good.
So Nathan has something less to do to help connect me with, yeah.
just to remind everyone that this is the first lecture, right? This is the introduction. So I guess you will learn the detail later on.
Yeah, you have all the experts. So
Yeah,
that
thanks,
means,
Rhea. That was a very
yeah.
good start. Even I really enjoyed your presentation.
I try my best to promote every one of you.
Thank you.
Yeah.
Yeah, and as you can see that there are so many questions in the chat. Even some have some opinions, and I think that was really good. This is a really good start. Okay, so Nathan, what to do next?
Okay, so we are at the end of the session, and thank you for attending, all of you. I think that will be our end of this, and don't forget to join if you want the introduction of Python in another 3 hours from now.
2 hours. I
So,
think it will start at 7,
oh
right?
yeah, sorry. Yeah, in 2 hours. So thank you all and see you. Bye bye.
Bye.
Okay,
Thank
thanks,
you,
Rhea.
Rhea.